Great. As I said, my name's Alfred Bresnik. I've been involved with TIMS from the start. There were two of us graduates from the University of New South Wales who were approached the by the professor who came up with this teaching concept, and we have for about 30 years commercialized this system. So I'll first of all give you an explanation as to what is the teaching purpose, what is the teaching method, and why we use this method within telecommunications courses. So the first point to state is say that, well, let me talk about the company. So before I talk about this modeling system. So our company is Imona Instruments. We're based here in Sydney, Australia. We're only a few kilometres from the centre of downtown Sydney, and actually we're located opposite the University of Sydney, which is the oldest university in Australia, and also power users of the TIMS system. So let me give you the background to the TIMS system that you can see behind me. So some time ago, a lecturer of Communication Systems 1 and Communication Systems 2 at the University of New South Wales, Mr. Tim Hooper, was put in charge of the communications course and the comms lab. And what he saw at that time was that students were spending quite a bit of their time building electronic circuits or writing software code before doing the communications experiments. This he didn't like because he said he had a lot of topics to cover and only a limited amount of time. So he didn't want his students building electronic circuits and debugging them before doing the communications theory experiment, or writing code and debugging it before doing the communications experiment. So he looked around, and what he saw mainly was either software simulation, or just as I'll use this book, or what we call single panel trainers, where one trainer might be analog modulation, let's say AM, single sideband, double sideband. Another panel trainer might be FM and phase modulation. Another panel trainer might be sampling and reconstruction, and so on. And he said these panel trainers are very interesting. The students can see signals, but so what? They adjust a few parameters. The students aren't involved in the theory that he was teaching. So he tried a number of different concepts. And TIMS was the result of this teaching method, which deeply integrated the mathematics and theory that he's presenting in his lectures with the actual practical labs, so that students would get a better understanding and feel for this mathematics and theory associated with telecommunications. More than that, he was also looking for a system where which was again more modeling based, so that it could expand. So as telecommunications theory develops over time, experiments can be added without buying a whole new set of equipment. So this is the background to where TIMS came from and why TIMS came into existence. Before I show you Tim Hooper's teaching solution, we'll take a step back, a step above, and say that what Tim Hooper was particularly interested in was the fact that technology changes over time, as we've all seen, but the principles, the theory remains the same. And what that means is, the original probably long-distance communication was smoke signals, a bit like on-off ping. But seriously, the first real electronic communications was implemented with valves. And then technology changed to transistors. And then technology changed to ICs and today FPGAs and SDR. But what's common between the valves, the transistors, and the SDR? What is common is what Tim Hooper wanted to teach the students. So the engineer would have the underpinning and fundamental knowledge, theory knowledge, to apply this communications theory to whatever technology. And here is what the theory is. This is the block diagrams, the common language, the international language of telecommunications. So it's that theory that Tim Hooper wanted to focus on, and not so much the implementation at this stage. Later subjects, HF, UHF circuits, or microwave circuits, and so on, these are all different implementations of this theory that was being taught in subjects like Communication Systems 1 and Communication Systems 2. Because whatever the technology might be in the future, whether it's quantum computing or optical transistors or whatever, the theory that is being implemented is still the same. So what was Tim Hooper's solution? Well, his point was, he said, I'm already teaching students the mathematics and the theory, and all of this mathematics and theory is always expressed as block diagrams. So if you open any telecommunications textbook, any telecommunications paper almost, there'll always be block diagrams, because this is how communications engineers make sense of and understand what is happening. So Tim Hooper's solution was to say, in the block diagram, where there's a multiplier, which you can see up there, to have a real electronic multiplier block. Where there's an adder, to have a real electronic adder. So the TIMS system is exactly what I've just shown you, is many, many blocks which relate to that block diagram, and that's how the students build the experiments, by looking at the block diagram, doing calculations with the mathematics, and building the experiment. So each experiment is built by the students, step by step, in an engineering way, adjustments made and so on, so that the student can see what happens to those signals. So, as you can see here, there are blocks for signal source, adder, multiplier, phase shifter, blocks from the block diagram, and there are the TIMS modules, as we call them. And notice one important thing. No module is an experiment by itself. Every experiment is built by following the block diagram. The block diagram is the instruction on how to build that experiment, that modulation scheme, or that demodulation scheme. So how difficult will this be for students to have to build each experiment? Well, Tim Hooper thought about this and developed the system in such a way that students can pick up modules and in most cases, start to use them without having to read the user manuals, because if TIMS follows very strict conventions. For example, here you can see inputs are on the left, outputs are on the right. Analog level signals, bipolar signals, are yellow, and you can see from the system behind me and here, digital signals are red. So immediately there's this convention. Another important point you can see in the slide and here in the webcam, notice that none of the knobs have any scale markings. This is intentional because we don't want students to set to 9 o'clock to 12 o'clock. We want the student to actually use use the measuring instruments to adjust the amplitude, the phase, the frequency, according to the theory that they have calculated, or maybe the simulation, the MATLAB or LabVIEW results that they've got, they adjust. So the student actually builds the experiment. So the positive side of this is, as professors have told me when they've taken TIMS or tried TIMS, they said, you know, Alfred, we understood what you said. We patched together an experiment, but it didn't look right. It wasn't working, but we remembered that you said build the experiment step by step, adjusting each parameter, and then the experiment falls out. So the students actually learn these engineering concepts of adjusting, making adjustments, looking at signals, making decisions. Does this look right? Is this the value that I expect? Is this the value that was predicted? So the students are building the experiment. So if you have, the downside is, if you have lazy students who haven't done any preparation and just willy-nilly patch together an experiment, the resulting waveforms will be valid mathematically, but may not be useful in a communications concept. And what I mean there, just as I can demonstrate this, is, for example, if you patch together something simple like AM and you don't care about the amplitudes and phases and frequencies, you may have the result that is the trigonometric result, the formulaic result that's correct, but you may have overmodulation, undermodulation, or different offsets. So the results are correct mathematically, but they're not useful. So you need to adjust it so that you have 100% modulation, so that you're not clipping, and that the appropriate message frequencies and passband frequencies are selected, and so on. So this gives you a very quick overview of where TIMS came from, what the teaching method and the philosophy behind the teaching method is, and how students actually use the system. So with that, I'm almost finished just this first part, and I'll ask for any questions. So you might look at this and say, well, okay, you're talking about some simple blocks. What can you actually do? Well, this slide shows you above in the white boxes is the transmission model, the message, encoding, modulation, channel, demodulation, decoding, and receive message. And under each of those, you can see the different encoding schemes that TIMS can implement. And under modulation, have a look. TIMS can do from the simplest modulation, which we would probably say is double sideband suppressed carrier, the multiplication of two signals, right through to the latest OFDM, 4G, 5G concepts. So TIMS covers a very, very broad range of experiments. What does this mean to you, the lecturer? This means that you look at your curriculum, you look at your course, and you can now choose those experiments that match your curriculum, those experiments that you want students to experience and to learn from. And not only does TIMS allow you to pick and choose the experiments, TIMS allows you to choose how deeply you want to go. You want the students to explore those experiments. Do you want the students just to qualitatively look at different waveforms, compare them? Or do you want the students to go much deeper quantitatively, to make signal-to-noise measurements, bit error rate measurements, coding gain measurements? So TIMS allows you in one axis to choose the experiments, and on the other axis, TIMS allows you to go to different depths for each experiment, obviously matching the time that you have for your lab classes. So this covers the first leg of this presentation. So please let me know. Do you have any questions at this point? Before the next step, I'll actually do some demonstrations and show you these modules in action. Do you have any questions? Please let me know. Am I speaking too fast? Is it does it all make sense? So, any questions?
Yes, thank you very much. Is Alex here, lecturer from communication engineering courses and signal processing courses at RMIT. Thank you very much for the presentation. It's very, I know a little bit about the teams. Just a little bit myself. I've been finishing my um, undergraduate and postgrad studies at RMIT Melbourne. And my background is communication engineering. And when I'm telling you this one, because I was working as a tutor, a laboratory demonstrator in Melbourne, RMIT Melbourne, before I came here to RMIT Vietnam. And I remember that was a long time ago, maybe 10 years or maybe a little bit 15 years ago. I worked with teams. I remember when I was a lab demonstration for the communication engineering courses in Melbourne, I used Teams. It was a long time ago. I remember there was a modules that you presented, and I can see you have a lot of modules here. I would like to ask you about the FM modulation. Most likely you have here, but I'm running the course here, and we have some AM modulation and FM modulation and digital communication. We're running 3 experiments. So I would like to maybe a little bit later to ask you more about the modules that you have it in, because I can see that you have a lot of modules there, and to see that which are the mostly useful modules for my courses, so that maybe a little bit later I would like to ask you more questions. Thank you.
Okay, fine. I will just I'll interrupt my flow just to address your FM question, for example. So because TIMS is a modeling system, we can actually implement FM in 2 different ways, both narrowband and wideband FM. We can implement FM with a VCO, the simplest way, or we can implement FM using the harmonic multiplier technique, where we have bandpass filters and work at 33 kilohertz and then 100 kilohertz and so on. So with TIMS, it depends how deeply do you want to go into the FM experiments. So you can do simple FM experiments or more complex FM experiments. And what I would answer you is, yes, we have a list of modules here. I'll just show you quickly. So there. So there's a list of modules. But as I said, no module is an experiment. What's more relevant is, let me go back here, are the actual experiments. So in your position in the first pass, unless you're really familiar with the TIMS experiments where you can tell us, I want this module, this module, this module, it probably makes more sense for you to tick the boxes here of the experiments you're interested in. And we can then tell you what's the minimum combination of modules you need to implement those experiments, so that we can then work in and iterate to get to a compromise of the experiments you need and the budget and the time you have to implement the experiments. So I would prefer not to give you module experiment tables where you have to work out, I want this experiment, I need these modules. You just give us the experiments you're interested in, and we'll then tell you the modules that we can work there, and that works much faster. So if that answers okay, I will go to the back to the presentation and do the practical.
Yes, thank you, because you have a lot of modules, and we would like to have that modules that we make in the experiment. So because we have a introduction, we have many courses. We have at this stage running communication engineering 1, which is introduction to communication engineering, and we have 2 AM experiments that I'm doing at this stage, and 1 with FM, and we have 1 with digital communication. And plus, I would like to just a little bit more add that in signal processing also, I'm teaching that course. I'm a course coordinator there, and there we have also some experiments that I think we can use TIMS for FIR filter. For example, we have FIR filter experiment, and also signal and spectra. So that's introduction. The students, they're learning a signal spectra, and after that going to doing an experiment with FIR filter. And that is also, I'm pretty sure I can see that what I looked at, you have a lot of modules which can be used for signal processing. Thank you.
Look, I will, after this stage, one of the topics I'll cover is I'll introduce, yes, the FIR and spectra and so on. There is a whole lab manual we have, which is some 300 pages, which is focused specifically on signals and systems experiments. So again, out of those 16 experiments, you can choose the experiments, whether they're spectra, whether they're Fourier, complex numbers, convolution, or FIR or IR filters. But in everything we do, all those experiments, I'll show you later, but I'll just like to say now, everything we do is hardware, not simulation. So the FIR filters that students build, they actually build them from blocks, not DSP. They're actually adjusting the gains, the coefficients, and delays and summing junctions and so on. They actually do this by hand so they can see that these continuous time and discrete time structures that they're learning about, the Laplace and the Z transforms, are not just mathematical abstracts. They're actually real life signals that they can actually see on the oscilloscope. So I will cover that, but that's just a quick jump.
Thank you.
So now I'll come back. I'll quickly go through this. This will be just very brief. If it's too quick, let me know. But just to give you, because I've given you the background of how TIMS works on screen and by waving my arms around, now I'll show you the real system. So